In the quest to unlock the mysteries of the universe, one remarkable instrument stands at the forefront of astronomical exploration: the James Webb Space Telescope, JWST. Launched on December 25, 2021, this cutting-edge observatory represents a monumental leap forward in our ability to study the cosmos, opening new windows into the universe's history, structure, and potential for life beyond Earth. The design and engineering of JWST are nothing short of extraordinary. Its large, segmented primary mirror spans an impressive 6.5 meters in diameter, about 3 times larger than Hubble's mirror. This extensive surface area allows JWST to collect more light and resolve finer details than any previous telescope. Each of the 18 hexagonal segments of the mirror is made from beryllium and coated with a thin layer of gold, optimizing its performance in the infrared spectrum. One of the telescope's most innovative features is its sun shield, which is roughly the size of a tennis court. This 5-layer shield protects the instruments from the sun's heat and light, ensuring that they remain at the ultra-cold temperatures necessary for infrared observations. Operating at temperatures below 233 degrees Celsius, 388 degrees Fahrenheit, JWST can detect the faintest signals from distant celestial objects, which would otherwise be obscured by the brightness of nearby stars. JWST's location at the second Lagrange point, L2, approximately 1.5 million kilometers from Earth, allows it to maintain a stable position relative to our planet and the Sun. This unique vantage point ensures an unobstructed view of the cosmos, free from atmospheric distortions and light pollution, making it an ideal location for astronomical observations. The scientific goals of JWST are as ambitious as its engineering is complex. One of its primary missions is to study the formation of stars and planetary systems. By observing the dense clouds of gas and dust where stars are born, regions like the Orion Nebula, Webb can provide unprecedented insights into the processes that give rise to solar systems, including our own. The telescope's ability to penetrate these thick clouds with infrared light enables scientists to observe the earliest stages of star formation, where protostars are hidden from optical telescopes. JWST also aims to explore the atmospheres of exoplanets, planets orbiting stars beyond our solar system. By analyzing the light that passes through an exoplanet's atmosphere during transits, scientists can identify chemical signatures that may indicate the presence of water vapor, methane, and other key molecules associated with habitability. This capability places JWST at the forefront of the search for extraterrestrial life, offering a new means of identifying potentially habitable worlds. In addition to studying individual exoplanets, JWST is designed to survey large numbers of them. This statistical approach will help identify trends and patterns that could point to the prevalence of Earth-like conditions in the galaxy. By understanding the diversity of planetary atmospheres, we can better assess which worlds might support life as we know it. Another major objective is to investigate the evolution of galaxies. By looking back in time to when the universe was only a few 100 million years old, JWST will help us understand how galaxies formed and evolved, revealing the history of cosmic structures and the interactions that shaped them. The telescope's ability to capture detailed images of distant galaxies will shed light on phenomena such as galaxy mergers, starbursts, and the role of dark matter in galactic formation. The advanced technology behind JWST is a testament to decades of research and development. Its infrared instruments include Near-Infrared Camera, NIRCam. This camera is crucial for capturing images in the near-infrared spectrum, enabling observations of the first galaxies and star formation regions. NIRCam also serves as a wavefront sensor, helping to align the telescope's mirror segments with extreme precision. Mid-Infrared Instrument, MIRI. MIRI extends observations into longer wavelengths, allowing scientists to study cooler objects such as brown dwarfs and to analyze the chemical composition of exoplanet atmospheres. Its ability to detect the thermal emission of distant objects provides insights into their temperature and composition. Near-infrared spectrograph, NIR-SPEC. This instrument can simultaneously observe multiple objects, capturing their spectra to reveal their composition, temperature, and velocity. By studying the light from distant galaxies, astronomers can learn about their formation and evolution. Fine guidance, sensor, near-infrared imager, and slitless spectrograph, FGS, NIRIS. This combination provides precise pointing and allows for spectroscopy of exoplanets, enabling scientists to analyze their atmospheres in detail. JWST's ability to operate in the infrared spectrum is crucial for several reasons. First, many celestial objects emit most of their light in infrared wavelengths, particularly those that are very distant or cool, such as young stars and distant galaxies. Second, the expanding universe shifts the light from distant galaxies toward the red end of the spectrum due to cosmic expansion, a phenomenon known as redshift. JWST's infrared capabilities enable it to study these objects more effectively, revealing the universe's history over billions of years. After months of commissioning and calibration, the world eagerly awaited the first images from JWST. When they finally arrived in July 2022, they took our breath away. Stunning deep-field images revealed thousands of galaxies, some of which are over 13 billion light-years away. Each picture is a snapshot of the universe's history, showcasing not only galaxies, but also intricate details like star formation regions and cosmic dust. The deep-field images captured by JWST are among the most detailed ever taken, providing a glimpse into the complex structures and interactions that define our universe. Among the remarkable discoveries made by JWST are new insights into the life cycles of stars. Observations of the Carina Nebula, one of the largest star-forming regions in our galaxy, unveiled previously hidden details about newly formed stars and the intricate structures of gas and dust that surround them. These observations provide a glimpse into the early stages of stellar evolution, enhancing our understanding of how stars and planetary systems develop. JWST's findings are not limited to distant galaxies and star formation. It has also contributed to our understanding of cosmic phenomena closer to home. For instance, its observations of the atmospheres of Jupiter's moons, such as Europa and Ganymede, provide insights into their potential for hosting life. The telescope has also captured detailed images of Saturn's rings, revealing intricate structures and patterns that enhance our understanding of this iconic planet. The impact of the James Webb Space Telescope extends beyond its scientific findings. It symbolizes international collaboration, with contributions from NASA, the European Space Agency, ESA, and the Canadian Space Agency, CSA. This cooperative effort highlights the shared human endeavor of understanding our universe and our place within it. By pooling resources, expertise, and technology, these agencies have created a telescope that pushes the boundaries of what is possible in astronomy. JWST's public engagement initiatives aim to inspire future generations of scientists, engineers, and explorers. Educational programs and outreach efforts are designed to make its discoveries accessible to all, fostering a sense of curiosity and wonder about the universe. The telescope serves as a reminder that the pursuit of knowledge is a collective journey, one that transcends borders and unites humanity in the quest for understanding. As JWST continues its mission, it is set to revolutionize our knowledge of the cosmos. From the formation of stars to the search for life on distant worlds, The telescope's discoveries will inform and inspire generations to come. Its ability to observe distant galaxies will illuminate the processes that govern galaxy formation and evolution, helping us piece together the history of the universe. Future observations will focus on the early universe, allowing scientists to study the first galaxies that formed after the Big Bang. By understanding the conditions that led to galaxy formation and the emergence of cosmic structures, we can gain insights into the fundamental nature of our universe. These observations will not only deepen our understanding of galaxy evolution, but will also enhance our comprehension of dark matter and dark energy, two of the greatest mysteries in modern astrophysics. JWST's legacy will also encompass studies of stellar populations, star clusters, and the dynamic interactions between galaxies. Its ability to conduct wide-field surveys will allow astronomers to catalog thousands of galaxies, exploring their diversity and evolution over cosmic time. The James Webb Space Telescope is more than just a scientific instrument. It is a beacon of human curiosity and ingenuity. As we look to the stars, it invites us to ponder the deeper questions of existence. How did the universe come to be? Are we alone in the cosmos? With each observation, JWST brings us closer to answering these age-old mysteries, reaffirming that the journey of discovery is as boundless as the universe itself. In the coming years, JWST will continue to redefine our understanding of the cosmos. Each new discovery will enrich our knowledge and expand our perspective, reminding us that the universe is a vast, intricate tapestry woven with threads of mystery, beauty, and wonder. As we continue to explore this cosmic frontier, we are reminded that the search for knowledge is a journey that is as infinite as the stars themselves. With every image captured, every spectrum analyzed, and every secret unveiled, the James Webb Space Telescope reaffirms our place in the cosmos and inspires us to dream of the possibilities that lie ahead.